All right, so let's look at number 3. Start with the maxes and mins, and everything else will fall out. Like, especially the concavity. Like, you already think about this one up here, and I paid attention to when f prime is increasing the whole time, therefore it's concave up the whole time. But really, if all I knew that there was a min here, how else would I draw it, right? You would draw it like that. All right, so the concavity is not really going to be the sort of determining feature. The maxes and mins are. So what you're going to do is you're going to start by looking at your f prime. This is f prime every time in red. Okay, we know that because it says the graph of f prime is shown. All right. Look for where f prime changes positive to negative and draw a max there. So positive to negative is a max. We could draw the max down here if we wanted, but let's give ourselves room to draw and put the max up here. Remember, we don't know the y coordinate. We only know the x coordinate. All right. We also know that f prime changes from negative to positive right here at x equals 3. So we're going to have a min there. We also know that since f prime is positive on both sides of this, f prime has to increase all the way up to x equals negative 3, and f has to continue to increase after x equals 3. It can't do anything else. In between x equals 3, negative 3, and x equals 3, in between there, f prime is negative, so the graph has to be decreasing. But if you think about it, just putting this max and the min here and just connect them in a logical way, and everything else is going to fall out, right? So I've already got, how else are you going to connect this without decreasing from negative 3 to 3? So find your maxes and mins, connect them up nicely, and that's going to be the graph, all right? You can think about the concavity. F prime is decreasing up to 0, so I should be concave down up until 0. And then f prime is increasing after 0, so f should be concave up. But see, concavity is a little bit vague in terms of the graph. Who's to really say exactly where this graph changes from concave down to concave up? It changes somewhere in here. We could indicate somehow that it changes here. This is the point of inflection. The point of inflection where the concavity changes from concave down to concave up. All right, but points of inflection are going to be sort of up for grabs on the graph because it's generally not clear from looking at a graph where that point of concavity is. All right, now let's look at number 5 here. So I'm doing the odds, saving the evens for you. So what have I got? I've got a min where f prime changes negative to positive, so let's put a little min there. I've got a max where f prime changes positive to negative, so let's put a little max there. I don't have to put the mins below the x-axis and the maxes above the x-axis, but why not give myself some room to draw? I'm going to put, it looks like this is supposed to be x equals 1, 2, 3, 4, so let's put our other min here at 4. By the way, the two mins do not have to be at the same level. They could be greatly displaced. We don't really know that, all right, without plotting some points from a graph. All right, so now let me show you how once you've got the maxes and mins in, just connect them up. Bing, 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 bing. There's not really any other way to connect those, all right? And make it look like a polynomial graph. Look, f prime looks like a polynomial, so f is going to look like a polynomial, all right? But if you want to like really break it down and say, where is f prime negative? F prime is negative from, looks like 0 to 4 or whatever that is. Well, f is decreasing from 0 to 4. F prime is positive from negative, is that 4? Negative 4 to 0. So f is increasing from negative 4 to 0. Like those things are going to happen just because I connected up the maxes and mins. And if you really want to say, ooh, f prime is increasing up until x equals negative 2, well, f is concave up until negative 2, and then f turns concave down. That all came out without my thinking about it. Think about the maxes and mins, everything else comes out. Here's another useful guideline. Do you remember how we said that if f prime is a polynomial of degree n minus 1, then f is a polynomial of degree n? So that means that f is always a degree higher than f prime, assuming f prime is a polynomial, which these graphs look like polynomials, so let's treat them like polynomials. This one's linear, so f prime is linear, f is quadratic. F prime is quadratic, f is cubic. F prime is cubic, f is quartic. And so you want to, this is why you spent so much time in Algebra 2 and pre-calculus knowing what those kind of graphs look like. That a 4th degree graph has up to 3 turns. A cubic has up to 2 turns, but it doesn't have to have 2 turns. Okay, so there's those three. Let's look at some of the peculiar ones, shall we? You can get 2, 4, and 6 based on those models. Let's look at some peculiar ones. Look at number 7. What do you think about number 7? Take a think about number 7. What do you think the graph looks like? Okay, so we know that since f prime is constant, so it's degree 0, f is going to be degree 1. It's going to be linear. We also know that what this is really saying, since this is a graph of f prime, okay, f prime is the slope of the graph, and the slope of the graph is constant. Not only is it constant, but we know what it is. It's 1, 2, 3. It's constantly 3. So f has a slope of 3. So it goes up 3 over 1, up 3 over 1, up 3 over 1. All right. So I know not only that the slope is constant, but I know what the slope is. So we know kind of a little bit more than usual about what the graph looks like. But remember, since this is not the only graph that has slope 3, right? We could draw this graph with slope 3. Oops, that's not very slope 3. All right, let's say that's slope 3, all right? Or I could draw this graph with slope 3. I could draw any graph with slope 3. They're all going to be parallel because the derivative is invariant under vertical translation, and all these graphs with different y-intercepts but the same slope are vertical translations of each other. All right, with that in mind, let's look at number 8. So number 8 is also constant function, but it's different because it's constantly 0. So what that means is that the f, all right, f prime is constantly 0. That means the slope of f is constantly 0. So f is a constant function. F could be the same function, all right? Or it could be negative, it could be anything. But we know when f prime is constantly 0, that f has constantly a 0 slope. Therefore, f is a constant function. All right, let's look at another weird one. Let's look at this one. All right, so in this case, look what's going on. There's like a jump discontinuity in the derivative, remembering that this is f prime. You know what, we're going to save that for the next video because it's weird and we have to talk about a whole new thing. So we'll look at number 9 and 12 next, and then we'll look at number 13, and you get to do the rest of them. All right, you should think though about number 9. What do you think it should look like before you start the next video?